Oh, thank you. Okay, today, let's see, I'm going to do a couple of odds and ends. I guess first I'll answer questions that you might have run into in the baby steps. And then if there aren't any questions or we run out of questions, then what I'm going to talk about today are recursive function calls, which is an application of stacks. And if we have time, I will get into binary operations, where the bitwise operations of binary operations is not the right word. The bitwise operators, because the next assignment after this is writing something called a bitstream class that lets you write individual bits to a file and read individual bits from a file. If you don't know a whole lot about reading and writing files, you should know that the minimum addressable space in most computer operating systems is a byte, 8 bits. And so to be able to write a single bit at a time to a file requires you to essentially buffer the reads and the writes into bite-sized chunks, and then when a byte fills up with bits that you're interested in, then you flush it out to the file. So we'll write a class that will allow us to write individual bits to a file and read individual bits from a file. And then that will be followed immediately by a program that does data compression using what's called the Huffman compression algorithm. And the Huffman compression algorithm is the foundation of nearly every compression algorithm that you run into out in the real world. So it's really a foundational kind of thing to learn. That said, I'm not teaching the Huffman compression algorithm really to teach you about Huffman, although it's super cool. I'm teaching you the Huffman compression algorithm to introduce you guys to trees. Trees in the graph theoretic sense, not trees as in the forest sense. So that's a map of the next couple of weeks. You guys have an exam coming up Friday, and what we'll do is we'll talk a little bit about it on Wednesday. I'll give you should be looking at, for example, the reviewing the readings from Gashard's book that I've assigned, and you should be reviewing the self-test exercises in Savage in the sections that I've assigned. I'll also provide you on Wednesday with just a couple of sample problems, so you'll have an idea of what kinds of problems I might put on the exam on Friday. The Friday exam will be entirely in class and will be designed to be completed in 50 minutes or less. You'll be writing answers longhand, yes. I'm not a stickler about C++ syntax when you're writing things longhand. I'm mostly looking for just the order of events, and so I may ask you to write a snippet of code to do some particular thing, but I'm not looking for every curly brace and every semicolon, just the general idea that you've initialized the variable before you've used it and things like that. Jamie?
Well, I mean, would you want us to do like cout, caret, or do we just do like?
You can, as long as you convey to me that you're printing something to the screen. And I think for 99% of you, it's going to be just cout less and less than. But if you don't remember the exact syntax, then you can just kind of sketch it out, what you're trying to do. All right, questions on the homework? I know Luke had one. It's hard to answer some questions because it gets so specific, but if you have some questions, I'd be happy to.
So you implemented two objects, token and operator. And I was just thinking about it. It seems like I was thinking, like, if I sat down to do this, I think one class that had a member function that grabbed whatever came in off the stream and then either set it as an operator variable or just, oh, it's a number, pushed onto the stack. So I don't really see the purpose of having both classes,
Mhm.
and I was wondering, since you have both classes, at what point in the program, when you pull an operator off the stack and the token becomes an operator, does that become an actual operator object? Is the operator class a friend class of the token class, such that you can do that internally in the member functions?
So I think in my program, getToken was responsible for identifying the operator and pushing it onto the op stack. The reason I wrote it the way that I did was with an eye towards extensibility, with an eye towards adding additional operations. And I tried to compartmentalize as much of the operator execution as I could away from the tokenizer. So I'd have to look at my program again to see how successfully I did that, but I think they're fairly well dissociated in the sense that if I want to come along now and add tangent to it, I have to make almost no changes to my tokenizer other than just identifying the string tan. And then everything else happens in the operator object. That was my goal when I did it. As I mentioned earlier, you can feel free to not use any classes at all. You can very easily do this with functions that are inside. You've got main.cpp, right? And you've got stack.cpp and stack.h. You could very easily do this with those three files, just defining functions inside main.cpp that parse the command, the input stream, and execute objects. As I mentioned earlier, I did it with objects because it was very early in my C++ career, and I just wanted to try some objects. But my philosophy, I think, is what you're getting at. My philosophy was to keep the tokenizing and the operator stuff as far apart as possible.
So then, do you give the tokenizer privileges to declare and define operators inside its member functions?
The only thing the tokenizer can do is identify operators. And by that I mean give opcodes, like essentially grab the next token and give it an opcode.
Okay, so you just have like.
And then all the opcode stuff is in the other class.
So do you have like a sequence of code where the tokenizer reads something off the stream, returns in a member function like the opcode, and then you use that opcode as the input for an operator member?
Pretty much, yeah.
Okay.
Let me in my main, I use this. Return the most recently read opcode.
Where are we?
See the cursor?
Okay. Okay. So you have a private variable we can start with that.
Right, and the only thing so when I add a new operator, the only thing I have to do to my tokenizer is tell it how to identify the operator, how to get from the characters to the opcode.
Right.
And then the action of that operator is defined in the operator class. Right? What does tangent actually do? What does addition actually do? All of that stuff is in the operator class.
Let's say we just do this without making any classes, just do it functionally, which is actually, you can be organized, but when we typically submit our assignments, you want a makefile with it.
Absolutely.
So there's just one, you just want us to, in the makefile, type G++.
Well, remember your makefile is going to have stack.
Well,
unless you're using the STL. In that case, yeah, just still give me a makefile.
Okay, that's what
Yes, absolutely. Yeah, because I gave you the option last time of using the STL stack, and that's still there. Okay.
What would be the
best or recommended way to do like some kind of like global variable, like the E error code that we had in the first program, without passing it into every function or adding that? Can we make like
so you just want a global variable? Yeah. So you can put that. You can either put that in, probably the best place to put that would be in main.cpp, outside of main. And then it'll have global, it'll have, well, depends on how you're doing things. If you're doing things with functions, then in main, then putting a global variable E in main.cpp will then have scope into all the functions. If you're doing it with classes, you're going to have to work harder because you're not going to be able to get the global variable to reach inside your classes.
Can't you just use assertions to get basically the same functionality?
Yeah, the problem with an assertion is, and I don't remember, did I ask you to just have it continually ask for expressions until it quits?
Probably.
I did. The problem with an assertion is it's gonna stop your program.
Oh, if you
Assertions stop the execution of the program immediately, and so I think Ben's approach is probably more robust. You set an error code, and then if that error code is lit, then you print out a message, but you don't crash the program. You just start over again.
create like if you're doing it with classes, might you create a private variable in every class that you can then set as a part of the function without passing it in and out of functions?
I think, I don't remember, let me check the private section here. I've got an error code here. I think I have an error code in the other one too. Yeah, I had an error code in here too, so that let's say I'm implementing a square root function and somebody tries to do a negative number. I'm not going to crash, I'm just going to set the error code. So before I try to do the square root, I'll check, is the argument negative? If it's negative, set the error code and leave, and then I have something in the main program that's checking that error code.
Do like can get errors.
Yeah, I think good.
Oh.
So I'm constantly checking, good? Good? Are we good? Yeah. And so I think if you're going to go with objects, you want to tuck an error code into each class. Other questions, comments? Anybody get any baby steps going? Raise your hand. Oh, good.
It's my stack class.
I'm so glad. Okay. When class is over, I can answer specific and perhaps more nitty-gritty questions that you might have. All right. Let's talk a little bit about recursion. So I'm asking you to read Savage 14.1. I'll probably ask you to read 2 and 3 as well, 14.2 and 14.3. But why am I doing this now? Recursion is hard to think about. It's not something that human brains are really good at. Some people are really good at it, and it's not something that is, some people are good at it sort of out of the box, but you can get good at it if you just sort of mush it into your head enough. You do start to be able to think about these things recursively, Jamie.
For the stack for evaluating operators, can you have that be a separate function and then have that be recursive to get rid of the whole, as opposed to having a while loop in the main program?
If you want, that's fine. That to me feels much more like a while loop. And do this until the op stack is empty. That just seems more natural. I'm going to talk about some stuff today. In fact, both of the examples I'm going to show you today are somewhat toy examples as well, that you would almost never do using recursion. But the goal today is to at least get your toe in the water of recursion now, and then I'm going to cycle back to it later, and we'll get a little more deeply into it, and then maybe even cycle back to it again a third time. And yes, that's a loop. That's not recursion. And I think if we spread this out a little bit, by the time we're actually using recursion, when we're doing tree traversals, which is where we're going to use recursion, and sorting algorithms where we'll also use recursion, by the time we get there, you'll have a certain level of comfort with the notion. And it's also relevant to the data structure that we've been working with for the last 2 weeks, and that's the stack. How does a compiler and how does a program actually do a recursive function call? All right, let's Okay, so a recursive function is a function that calls itself. And some languages don't even allow recursion. I don't know, Josh, is Java? Java okay with it? Okay. There are some languages that don't allow it, and I can't think of one off the top of my head. Most modern languages do. Sorry?
Fortran.
Possibly Fortran. I'm guessing Fortran 77 probably doesn't. But it might.
Pascal does.
Does Pascal? Yeah. Anyway, most languages do allow this. Here, I'm going to talk about the example that's in Savage 14.1. So we want to write a function. It's called write vertical. And what this does is it takes the digits of n. For example, let's pretend that n is 321 or something like that. It'll take that thing and it'll output 3, 2, 1. This is a toy problem. This is not the way that you want to print the digits of an integer vertically. I'd probably just push all the characters onto a string and then do whatever I want with them. But let's talk a little bit about this. If you want to print 3, 2, 1, what you can do is print 3 and then print 21 vertically. And then to print 21, you can print 2 and print 1 vertically. Whenever you have a problem, whenever you have a task that's designed like that, that's suggestive of recursion. So let me talk you through that again. So if I want to print 321 vertically, that's the same as printing 3 and then 21 vertically. And that's the same as printing 2 and then 1 vertically. All right. So let's see how to accomplish this. This is going to take a single integer argument. If n is less than 10, we are going to just print the number. Otherwise, we will call the function. Oh, and I was saying that backwards. I'm sorry. I'll rephrase that. It doesn't really matter, but the way that I'm writing this function is slightly different. All right. How was I saying this backwards? The way that this algorithm is going is, let's say n comes in and n is less than 10. Why is n being less than 10 important? That's one digit. So just print the digit. Otherwise, we're going to call right vertical on n/10. What does n/10 effectively do? Close. Gets rid of the ones digit. So it takes 321 and turns it into 32. Right? 32? Okay, so now we've called right vertical on 32. The current function halts there because it doesn't know what right vertical is going to turn into. So again, we're doing this on 321. We come in, 321 is not less than 10, so we call right vertical on 32. Now we go back up to the top. 32 is not less than 10, so we call right vertical on 3. 3 is less than 10, so write it. You get the 3. That function has now ended, and you're back at what level? You're at the 32 level, right? You're at the 32 level? Sorry, I just lost my place now. So that turns into 32, and we print out n%10. 2. And now we're back at the 321 level. And did I mess that up? Yeah, that's okay. And then you print the 1. So %10 is picking off the ones digit. Okay? So /10 is getting rid of the ones place, and %10 is pulling out the ones place. They're kind of complementary that way, and that's what this is taking advantage of. What happens, why this is a stack, is there's something called a runtime stack. And what this has is kind of all of the memory / symbols of the current state of the program. So you can think of this layer. Right, and in this layer are variables, function names, etc. Memory, other memory. Okay, now you're cruising along, and this stuff, values are changing, values are being added together. Maybe memory is being allocated and deallocated, all in this one stack. And then you get to a recursive function call, and the whole damn layer freezes. And what happens is a new layer is put on top. And this is for the recursive function call. And depending on how many recursive calls are actually active at a particular time, this thing can go up pretty far. When you get to the stopping criteria, okay, what's the stopping criteria for this recursive function?
If the if is true.
n less than 10, exactly. That's the stopping criteria. So you get up to the stopping criteria level, in this example, n less than 10. This guy, you don't have to push another layer onto the stack because this guy can actually run to completion. When this guy runs to completion, it goes away, and then the next layer can run to completion, and it goes away, and the next layer runs to completion, and it goes away, all the way back down to the bottom of the runtime stack. Go ahead.
A slight aside about our write vertical. Could you change all the 10s to 2s, and would that be a way of writing it in binary? It seems like you would go and you'd have the same criteria for the first thing, and then you'd be dividing by 2 to get rid of the top power of 2, running that recursively, and then printing the last digit.
We could test it.
Yeah, I want to do that.
The vertical thing is not really all that important, but whatever.
I mean, to make it not vertical, you could just not
Get rid
put
of
it
that
in
and
lines.
yeah.
Or even better, you can have it give a modulo argument.
Yeah, exactly.
And then include hex. It's like,
Yeah. That would just tell it how to do it.
yeah, no, you can figure it out.
Do I want n less than 2 or n less than 1?
And less than
2, because it needs to print
Just
1 or 0.
1 or 0.
Yeah. And eventually it's going to mod out to be 1 or 0.
Wait, less than 1?
Less than or equal to 1.
Yeah, less than equal.
Because then you're saying
Yeah.
n is 0.
That seems already to me to suggest that this isn't going to work. So I have to think hard about this now.
Isn't
Because-
the same thing that in the 1's digit of a base 10 number, you need something between 0 and 9. In the 1's digit of a base 2 number, you need something between 0 and 1.
You can make this work, it's just going to be a little. I think it's
I'm concerned that when I get in here, that's probably okay. Let's just try it.
Do some easy ones. Fine.
Yeah, we'll do something that we get. Else right vertical binary vertical. Thank you. n/10.
Function names. You might have gotten it confused with all the other functions in our program.
Have you been watching oh God, what's the name of that movie? The heavy metal rock band, Spinal Tap. Have you ever seen it? No, anybody?
Yeah.
So I'm glad you called it Yngwie J. Malmsteen to distinguish it from all the other Yngwie Malmsteens on the record shelf. It's one of my favorite lines in that movie. See out n%2. What's a good one?
5101.
Oh, wow, I got rid of oh, what did I do? Oh, yeah. It's above the stupid,
Why doesn't it just build those into the...
Nice. And there was much rejoicing. Okay. Good job, Luke. We can generalize this to any base just by tweaking the 2 or the 10, as the case may be. I'm just following the book. Okay. So I guess the thing to think about here is just, can you visualize what's going on vis-a-vis the runtime stack? So the thing runs, right? You call it the first time, and this is the bottom of the runtime stack. The main function is the bottom of the runtime stack. And whenever you call a function, whether it's recursive or not recursive, you actually put a new layer on the runtime stack for that function. Because remember that the internals of any function are really just, you can do anything inside a function that you can do inside main. And the cleanest, safest way to handle that situation is to really, when you call a function, to build just a whole new environment for that function with its own local variables, its own functions possibly, its own everything, its own memory. And then when that function exits, the results of that function are returned to the bottom, the stack underneath, via the return statement, or via reference variables, passed by reference variables.
Is that how local variables are taken care of?
It's exactly how they're taken care of, right? So what happens is I call the function and a new runtime stack is built, and part of that runtime stack, a new layer in the runtime stack is constructed. And part of that layer is memory for local variables. And that's why when the function ends, those variables are gone, because that layer is popped off of the runtime stack and you're back down onto the stack below. And languages that have this runtime stack can do recursive function calls. And really the only limit to a recursive function call is just running out of memory in the machine to accommodate the layers in the runtime stack. All right. So you've seen one. Let's think about another one. Another toy example. Again, I would never write this function this way, but so remember factorial. N factorial is n times n minus 1 times n minus 2 ... down to, say, 3 times 2 times 1. So that's the pattern. You just take all the numbers from n, all the positive integers from n down to 1, and you multiply them together. That's n factorial. How can we think of this as a recursive problem?
Factorial calls n minus 1 factorial if n is greater than 1.
Okay. It's got to do a little bit more. So what's going to happen? It's got to do something else.
Yeah.
Well,
also
it
has
needs
to
to do
multiply what you have by the next call.
So I'm gonna say n factorial. Right. This is factorial n. Right. That's the same as n times what?
That's right. Yeah.
And of course, that's the same as n minus 1 times factorial n minus 2, etc. And you can kind of see the runtime, the layers on the runtime stack here developing. What's the stopping criteria? If n equals 1, what should I do?
Return input. Return 1.
Oh. Okay. Should we also put in the condition n equals 0, return 1?
Well, I was going to let us discover that we had actually made a mistake, but you actually want to do that. That's a technical detail that many of you may not remember, but 0 factorial is defined to be 1. So you actually want to run this thing all the way down to 0. And if n is equal to 0, we're going to return 1. Because 0 factorial is 1. Let's see if we can write this. Before you talked about a raise?
Before talking about a raise, yeah. To keep it so on really short.
That's really dumb.
It's no, I mean it's fine. Whatever. Okay.
It just came after.
What do you want to call this thing?
Factorial.
Factorial. What's its return value? Or return type? And what is its argument? Int n. And we're just going to write the function declaration and the definition up above here. Stopping criteria is, as we just discovered, n equals 0, returns 1. Else,
Return times factorial.
yeah, that ought to do it. Yeah. Factorial 5, what, 120? 120, is that right? Yeah. 6 is 7.
720.
Is it 720? Okay.
That's going to be
Let's try 0.
5140.
Yay, 0. Let's try 1.
Can we just see what happens if
Sure.
Oh, it's going to not stop. Yeah.
So, I can speculate about what the segmentation fault is. I'm not sure about this, but so I was running this on my office computer. It's a Linux computer, and Linux, as I described earlier, is very protective of RAM. Right? You're allowed to do, like, I'm not allowed to write into system RAM, for example. I'm not allowed to read from system RAM unless I'm granted explicit permission. My guess is what happens here is you just start piling up layers and layers and layers on the runtime stack, and you run out of whatever permissible space you were granted to run this particular executable. When you get to that limit and you try to push that next layer, you get a segmentation fault because you try to access memory that you're not allowed to use.
Easy to see how many layers that is, right?
Yeah, we could put a print statement in there. Let's do that.
I think it's going to be a big number. Get it.
Let's call it level n.
Wait. Oh, right.
So that's how many layers I was allowed to put before it crashed. And we can see how many levels. We can try it like on 5. Oops.
How did you just kill
Wait,
it?
whoa. How did it let that go?
I'm sorry?
How did it let that go?
You didn't compile it.
Yeah.
So it called it with 5, then with 4, then with 3, then with 2, then with 1, then with 0. 0 is actually the stopping criteria, and then all the stacks collapse back down on themselves. Or not down, they just all get popped. Okay. Questions about that? Let me show you a slightly more interesting version of recursion.
It's really eerie that n changes within the function. You know?
Yeah. So this guy here is a binary tree. It's a binary tree because at every junction there are two branches. So here's 2, a left and a right. Then here's 2, a left and a right, and a left and a right, and a left and a right. Yeah, I know. I actually draw this tree recursively. And I'll just show you really briefly, and it's not really important that you totally get this right now. I'm going to get closer to this because I can barely see it. Need my glasses. So the recursive function call, it draws a branch. And the way that it works is, at each step, the branch is scaled down by 0.66. And as long as h is bigger than 2, I'm going to do this recursive function call. And when h is less than 2, that's the stopping criteria. So if h is less than 2, this whole if statement is skipped, and branch just exits quietly. If h is greater than 2, just ignore the whole matrix rotate translate stuff. You go through and you draw the branch. And the left branch, let me think about this. No, the right branch. You draw the right branch, and then after that's done, you go in here and you draw the left branch. And so the way this will work, assuming I don't have my left and right screwed up, is the first time through, it's always gonna draw the right branch, but it's not going to be able to, so it's going to draw the right branch, but it's not going to be able to, so it's going to draw the right branch and the right branch. And then it's going to get to a point where the branch is actually short enough, less than 2 pixels, so it will actually draw the stupid branch. And at that point, the branch function skips, and then it backs up 1, and then it calls the next branch, and that's the left branch. And then it backs up 1, and then it's done with that guy, so it backs up, and then it draws the left branch, but the left branch goes to the right branch, draws the right branch, backs up, goes up to the left branch, backs up. Now it's done with that, backs up, and so on. And so this is a right, middle, left traversal, essentially, of this binary tree. Right, middle, left is the way it goes. What do I mean by right, middle, left? Let me find the picture here.
You should make an animation for a ding draw.
You could change that.
Oh yeah, I could. Yeah, that's a good idea. I will do that. So the way it's going to go is it's going to go right and 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 right all the way down here, then back, and then left, right, back, left, back, left, right, and so on. And just that's what it does. And it's doing this right now as we speak. I don't know, 15 or 20 times a second.
Whenever you open this web page, it just starts running that?
Yeah, it's running right now.
That's in processing, was it?
Yeah. What does this do? All this does is the higher the mouse, the smaller the theta, which is the angle between the branches. And so when I go all the way up here, the angle between the branches is small. And down here, the angle between the branches, like I can get the angle to be almost a right angle. And I would say the most natural looking tree is somewhere in here, at least to my eye. And getting green at the leaves.
You change the color from within this control grid.
Yeah, so when it's one step away from the stopping criteria, I change the color. So we can go look at that really briefly. And I still had to fight with processing about how it does colors. It took me a while to figure it out. But see that little if statement at the top of right after h greater than 2, right here. Here is if I'm one step away. So I'm one step away from stopping. I'm going to set the color to green. And then when I get down here, I'll set it back to black.
So the way this is working, are you actually drawing the right line or not until you reverse it back to it? Like,
I'm drawing the line.
Okay.
Yeah, I could do it either way. Let me think about what I'm doing. I'm drawing the line before the call. So I'm drawing the line first. But I could have done it afterwards and not changed it. In fact, let's really briefly, let's go back to the vertical guy and think about something, a little variation on the vertical guy. What would be the effect of doing this?
Upside down.
Put it the right way and then the backwards way? Or backwards?
Oh, we're still in binary mode. Do I have a regular one? I don't have a regular one, do I? Yeah.
Find your place. Better change the function names, you know, otherwise.
So that's above, here's below. So yeah, you're right, it reverses the order. Do you have a good grip on Y? And if you don't, you should think about that. That's my little recursive homework assignment for you. This is just the point of today's discussion was to just get a little taste of recursion and see how it's related to stacks and when a program is running. What I'm going to talk about next time, and if you want to read ahead, let's go to the syllabus here. This guy has a relatively nice summary of bitwise operators in C and C++. And the big idea is right here, is encapsulated right here. Let me blow this up a little bit. If you have two strings of binary digits, what you can think of is these are 2 bytes. Remember, a byte has 8 bits in it, so these are 2 bytes. I can AND the bytes together, and what you get is a pairwise ANDing of the bits. So this and this, you AND these 2 guys. This is false, true. False and true is false, right? And then you AND these 2 guys. False and true is false. All these guys are false except for this guy, right here. True and true is true. All the rest of them are false. And there's a similar one for OR. 0 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1. 0. So if there's a 1 in either slot, or in both slots, I get a 1 in the result. We're going to use these operators to write a class that will let us write bits to a file instead of bytes. That's where we're headed.
Does that integer and integer, is that works in the GCD? Because it does for that.
Gosh, I never thought about it before.
I don't think so.
It's
Because
gonna
if you had like
the-
1 1 1 1 0 and 1 1 1
Only if the
1,
GCD
Well, yeah, but that's
is a
the
factor
power
of
of
2.
two.
Power of two.
Exactly.
Okay.
If it's a power of 2.
Oh, because it converts to binary. and then-
Yeah.
Okay.
So it's essentially,
It doesn't do anything.
or not just a power of 2, but sums of powers of 2. I think.
So even.
Like I think,
Yeah.
I think for example,
3 and 9, it's not going to get you. Sorry. Yeah, it's sums of powers. Yeah, no, 3 and 9 don't work. Because 3 is 1 1 and 9 is 1 0 0 1, and that's going to get you a 1 as being the GCD.
yeah, it's not going to get you the GCD.
Yeah.
I agree with that.
Yeah.
It's going to get you the biggest sum of powers of 2 divisor, I think, of between the two numbers. And the biggest sum of powers of 2 divisor of 3 and 9 is 1, 2 to the 0.
That's true.
So I'd never thought about that before, but I will think about that because you might be able to get some interesting stuff out of
10
that.
and 3 returns 2.
10 and 3 returns 2.
Unbelievable.
Oh
yeah.
I don't know if a bitwise calculator.
Oh no, that makes that makes sense. Yeah, that makes sense because
Yeah.
So this is just a coincidence then.
Yeah.
Okay, we'll just leave it at that. But I'll think a little bit about that. I'm done. If you have questions about your expression parser, feel free to come on up and